Hello everyone. We are going to talk about our paper, Deep Polarimetric Stereo Depth Estimation. Stereo depth estimation is a classical computer vision task, playing an important role in many applications, including autonomous driving, robotics, and VR/AR. However, stereo matching methods using only RGB information normally struggle to handle textureless areas. The polarization camera is passive, which avoids the limitation of sensing range. Moreover, the polarization images provide surface normal information, which facilitates stereo depth estimation. The polarimetric methods are robust to the textureless case and can achieve better performance. Since the polarization images contain information about the surface normal, a natural question to ask is, can we estimate the surface normal directly from polarization information? However, inherent ambiguities exist in the polarization images. When estimating the surface normals, there will be multiple solutions for both azimuth and zenith angles, which is also known as azimuth angle ambiguity and zenith angle ambiguity. The azimuth angle ambiguity with a pi shift caused by the multiple solutions of the cosine function is called the pi ambiguity. The azimuth angle ambiguity with a half of pi shift caused by the unknown dominant reflection types is called the half of pi ambiguity. In order to handle the inherent ambiguities of polarization information, we adopt the ISO depth constraints instead of direct surface normal constraint in the network to bypass both the zenith angle ambiguity and pi ambiguity of azimuth angle, and construct a unified ISO depth cost with different reflection to handle the half of pi ambiguity of azimuth angle. The previous polarimetric methods normally struggle to handle the polarization ambiguities. These methods usually assume a smooth surface or controlled illumination, which is normally limited to object-level scenarios or specific capturing environments. Since the polarimetric and photometric domains maintain different characters of the scene, a straightforward combination may not fully exploit the multi-domain information. We need to solve the inherent ambiguities in the polarization information, including the azimuth and zenith angle ambiguities. Lastly, there are few real polarimetric stereo datasets that are sufficient for network training. We present an end-to-end neural network to predict the depth from polarimetric stereo images. Our designed DPS-Net can fully leverage the multi-domain similarity between polarimetric stereo images and solve the inherent polarization ambiguities. To better exploit the multi-domain knowledge, we extract per-pixel features from RGB and polarization images. Then, we construct the 3D correlation volume of RGB and polarization for all pairs of pixels at the same height. In addition, the ISO depth cost is calculated and introduced to integrate the geometric information. Finally, the correlation features and ISO depth cost are retrieved recurrently by the GRU-based update operator. We design a cascaded dual GRU architecture to fully exploit the multi-domain similarity and ISO depth cost for stereo depth estimation. In the regression GRU, the increment is regressed directly from the multi-domain correlation feature. In the optimization GRU, the ISO depth cost is injected directly and introduced in an indirect manner by the virtual correlation feature. This table summarizes the comparison between ours and other learning-based stereo depth estimation methods. On both the IPS and the RPS datasets, our method achieves better performance, which demonstrates the effectiveness of our DPS-Net. We also show the qualitative comparison of the IPS and the RPS datasets. Our method can produce more accurate disparity with sharper object boundaries and finer overall structures. We visualize the qualitative results of our DPS-Net and traditional polarimetric method. Our DPS-Net has achieved closer results to the ground truth. We show the qualitative normal estimation results of our method and polarimetric normal estimation methods. Our method can generate clearer and more accurate surface normal results. Thank you for listening.